Hey guys, so we're going to start chapter 8 and we're going to focus on solutions chemistry. So we're going to have to think a little bit about what that means for us. Most people identify a solution or they imagine a solution to be some sort of solid dissolved in some kind of a liquid. And usually, and what we'll focus on anyways in chapter 8, people imagine water to be the liquid. So what they're really thinking is they're going to take some solid, right? The solute is what we call the thing that's present in the lesser amount in a solution, and they're going to dissolve it in a solvent. And when they're thinking about water being the solvent, what they're really saying is in that solution, the water is present in a greater amount. And by greater amount, what do we mean by amount? Well, when we get into figuring out concentration, we'll revisit exactly what we're talking about. We'll start actually with molar concentrations, and we will be focusing on aqueous solutions in this chapter, but you should know that a solution is simply just a homogeneous mixture, and it doesn't have to be a solid dissolved in a liquid. It does not have to be a solid dissolved in water. It can be anything present in a lesser amount, dissolved in anything that's present in a greater amount. In other words, a solute dissolved in a solvent. So I can have two liquids, right, that make up the solution. I can have ethanol dissolved in water. So the ethanol would be the solute and the water would be the solvent. I can have like a grape juice cocktail where I've got a whole bunch of different fruit juices dissolved in water. I can have beer. I can have whatever you want, right? So I can have a liquid dissolved in another liquid. And usually, instead of saying this thing is soluble, if you run into the term miscible, we're talking about a liquid dissolved in another liquid. We can also have solutions that are in the gas phase. So we can have a solution of a bunch of different gas, like air, for example, where the gas or the molecule that's present in the greater amount is nitrogen gas. And then there's a bunch of other little gases that are dissolved in it, right? So air, usually for us, is mostly nitrogen gas. And there's little bits of oxygen, because otherwise we would die. Sometimes we'll find some carbon dioxide in there, a little bit of methane, kind of depends, the environment that you're in. But you guys know that air is not a solid dissolved in a liquid, but it is a solution, right? It's just a solution that happens to be in the gas phase. You can have a solid solution. So if you went to the dentist in the 70s and the 80s, like I did, and got what we called mercury amalgam fillings stuck into your teeth, that's a solid, right? And it's a solution of a bunch of different solids. So dental fillings were mostly mercury. So mercury was the solvent. And the solutes, because there were a few other metals in the dental fillings, were usually tin and copper, and then sometimes trace amounts of silver. But they were usually about 50% mercury by mass, and then little bits of the other species. You could have a solution called brass. That's a solid. It's made up of copper and zinc. Pewter. I don't know how many of you guys know what pewter is, but some people like pewter jewelry. There used to be like, pewter cups and cutlery and all that kind of stuff. It was sort of all the rage a while ago anyways. But it's mostly tin with a little bit of silver, some antimony, bismuth, copper. But my point is that it's a solid and it's also still a solution. So we're going to focus on calculating solution concentration. And in chapter 8, we are going to spend time dealing with aqueous solutions. So in chapter 7, when we were writing out our reaction equations, if I had a species on either side of the reaction arrow and put a little parentheses after it and said, this is a little AQ, this is aqueous, what I was telling you was that that particular species is the solute and water is the solvent. So aqueous solutions are where water is being used as the solvent. And we can actually quantify the solution concentration. So before we do that, and we'll start with molar concentrations because they're the easiest and sort of the broadest category for us anyways in general chemistry, 31 anyway, will be concentration. And we kind of want to talk just a little bit about quantifying solution concentration, but first qualifying it with a picture here. And the easiest way to do that is to look at the change in color as we dilute a sample. So I've got glasses of cranberry juice here. And from left to right, you see that we start with our most concentrated sample. And it's really not hard to imagine that the most concentrated sample of cranberry juice would be the brightest red, and that the most dilute or the least concentrated sample of cranberry juice would be the lightest red, or almost the light pink that you see over there on the right. What we're doing is we're taking samples of our concentrated solution and we're putting them into other glasses and sort of systematically diluting them by adding more water. So, for example, if I took a sample of cranberry juice from that glass on the far left and I put it into the next glass over and then filled the glass the rest of the way with water, you wouldn't expect that the final solution would have the same saturation of redness, right? You'd expect it to be a little lighter. And if I took a sample of that resulting solution, put it into that third glass and filled it the rest of the way with water, you'd expect it to be even lighter, and then so on and so forth. So what we're looking at is a sample of cranberry juices, right? And they've each been sort of systematically diluted. We've been adding water to a sample of our previously concentrated solution each time. But how do you measure that? So how do you actually quantify the solution concentration? So we're going to start with our molar concentrations, because usually, at least in this class, our chemical reactions are going to be measured on a per mole basis, right? Sometimes they're measured on per mass, and we'll get into that. But right now we're going to start out with something called molarity. And the molarity of a solution is a measure of its concentration on a per mole basis. And what that means is we're going to take the number of moles of solute, whatever that may be, and we're going to divide it by the volume in liters of the entire solution. So the unit is usually a capital M. So let me highlight this for you, this big M right here. And that big M, very often in our calculations, it behooves us to sort of expand that unit, because big M is not very helpful. Big M is actually 2 units in one, and it's the moles of solute divided by the volume of the solution, and that has to be in liters. The other really important piece of information here is that we're talking about liters of solution. We're not talking about the volume of the solvent, right? So if I had, for example, a 2.50 molar aqueous solution of potassium chloride, that would contain 2.50 moles of potassium chloride in a liter of solution. And that solution is the potassium chloride plus the water, right? So if it's an aqueous solution, the water is the solvent, but the water is not the only thing in solution. The potassium chloride is also in solution. So we're not going to say, I've got 2.5 moles of potassium chloride per liter of water. We're going to say we have 2.50 moles of potassium chloride per liter of potassium chloride solution. That's going to be a big deal when we do our calculations. So if somebody were to ask you to prepare a solution like this, or a solution in general, you would want to say, I'm going to take, say, 186 grams of solid potassium chloride, and I'm going to add that to a volumetric flask with enough water such that the total volume is brought up to 1.00 liters. What you're not going to say is, I'm going to take 186 grams of solid potassium chloride and dissolve it in a liter of water. You are not adding a liter of water. You're adding enough water such that the total volume of the solution equals 1 liter. There's a big difference there. It may not seem like a big deal, but the 186 gram sample of solid potassium chloride actually takes up some of the volume. So you are not adding a full liter of water. You're adding enough water such that your total sample is 1 liter. All right, so let's do a few calculations and see how this rolls out. So starting with our first example here, it says, what is the molarity of a solution containing 72.8 grams of ethanol in 2.5 liters of solution? The first thing you're going to need to know is, what is ethanol, right? So what is the molecular formula for this particular compound? Because they're telling you that you have 72.8 grams of it. The issue with this is they're not telling you how many moles you have. They're giving you a mass. So if I know what the molecular formula is, I can figure out the molecular weight just using the periodic table, right? Sum up all the little parts that make up this ethanol molecule. And when I know that I have 72.8 grams of it, I can divide it by its molecular weight, and that will tell me how many moles are present in that particular sample. Then I see that I have 2.5 liters of solution. And I can divide those moles by the volume of the solution, and I will have the concentration of the ethanol in that particular solution. So ethanol looks like this. And yes, on a test, I would give you this molecular formula. I'm not going to expect that you know what ethanol is. But if I do give this molecular formula to you, I will expect that you can actually calculate the molecular weight. And this will be based on where everything's hanging out on the periodic table, right? So you're going to be looking for, I've got 2 carbon, so 2 moles of carbon atoms. I've got 6 moles of hydrogen atoms, and I have 1 mole of oxygen atoms. And so if I sum all of that up, I get 46.068, and I get another 8, but it's extra. I'm going to carry it anyway, so I don't have round off error. So I know that the molecular weight of ethanol is 46.0688 grams for every 1 mole. But I'm told that I have 72.8 grams. So over here, I'm going to start this off, 72.8 grams. I'm going to abbreviate ethanol just to save space. I'm going to call it ETOH, okay? Just to save us a little bit of space so that you know what I'm talking about as we work through the calculation. So if I want to know how many moles of solute I have, I need to convert this mass into a number of moles. So the number of moles of ethanol, ETOH, present in a 72.8 gram sample will be the 72.8 grams divided by 46.0688 grams per mole. So if I were to do this calculation and sort of end things right here, really what I'm telling you is how many moles you have in 72.8 grams of ethanol. But that's not what they're asking us to do, is it? They're asking us to calculate the molarity. And the molarity, big capital M, is the moles of solute per liter of solution. So in this case, we're talking about the moles of the ethanol, and the liters of solution are given to us. So if I want to know the molarity, I need to divide this by 2.5 liters. And what I get is 0.632. You can either say moles per liter or 0.632 molar. Very often you'll just see the answer reported as capital M, and that means molarity. That's the concentration. It's the molar concentration of that particular solution. So it's the number of moles of the solute divided by the liters of total solution. When do you report this as 0.632 molar. And when do you use 0.632 moles per liter? Well, if you were asked to calculate the molarity of the solution and that's the end of the story, then feel free. Or, if you're the person in the lab and you need to let someone know what the concentration of this sample is, and you just want to put a label on the bottle, then feel free to put 0.632 molar, big capital M like that, right? But if you're taking that concentration and you're going to use it in another calculation, it might be nice to break that unit up into moles per liter, because what if somebody wanted to know how many moles there were of ethanol in this particular solution and you had only a 42 milliliter sample? Wouldn't you want to convert that 42 milliliters into liters and multiply it by the concentration? If you had capital M, it would be a little bit more difficult to notice that you had to multiply by the volume because you don't see the liters in the denominator. See what I'm saying? Sometimes it's easier to just bust up the unit like that. So if you're going to use the number with its unit in a further calculation to make things easier on yourself, feel free to write moles per liter. If it's the end of the story and you just want to report the concentration, then capital M is fine. They mean the same thing. So let's try a different type of a calculation here. This next one wants you to determine the number of moles of the ferric ion in 100.0 milliliters of a 1.2 molar ferric sulfate solution. So here's the deal. The first thing you're going to want to do is you're going to want to convert probably this unit here, this big capital M, into moles per liter. So you might want to just rewrite that for yourself. The other thing you're going to want to note is, what is the ferric ion? Just remind yourself what it is. So it's iron with a positive 3 charge. And then the other thing you're going to want to note is, what is ferric sulfate, right? So if I've got the ferric ion, and I know sulfate has a negative 2 charge, when I bring these guys together, don't I kind of want to know what the mole ratio is? I really kind of want to know how many moles of that ferric ion are actually in that salt, so that when I go to figure out the concentration or the number of moles of the ferric ion in that particular sample, and I have the concentration of the total solution, don't I kind of want to know that, what if there's more than 1 mole per 1 mole of the salt, right, of the ferric ion? What if there's 2 or 3 or 4 or whatever? That's going to affect the number of ferric ions that I have in the solution, right? Because if there's 2 for every 1 mole of the salt, then 1 mole of the salt is going to give me 2 moles of ions, and that's going to affect the number of moles of those ions in that sample. So I kind of want to draw this out. When I bring these guys together, I have 2 moles of the ferric ion for every 3 moles of sulfate. And so that's going to be important, right? So I just set this up. I am told that I have 100 milliliters, and it's 100.0 milliliters of solution. That 0.0 is significant. I also know that I'm given a concentration, and that concentration is molar, right? It's the molarity. So it's 1.2 moles per liter, right? It's 1.2 moles of ferric sulfate, not the ferric ion, ferric sulfate. This is why we went through figuring out what the mole ratio here was. So I need to figure out how many liters this actually is. Not going to be convenient to stay in milliliters. So I'm going to convert the milliliters. So these milliliters are going to cancel out, and I'll have however many liters that corresponds to, right? So 100.0 divided by 1,000. So now I know how many liters of solution I have. What am I actually talking about? I'm talking about a 1.2 molar solution. So I'm talking about 1.2 moles of this salt in a liter of solution. Here's the deal. I don't have a liter of solution, do I? I have 100 milliliters. So I technically have 0.1 liter, right? 0.1000, because all of those zeros are significant. But the solution I'm talking about, the concentration is 1.2 moles per liter. If I only have 0.1 or a tenth of a liter, do I have a full 1.2 moles? No. So that's what's going on here. So now my liters are going to cancel out. And I have, essentially, as I work my way through this calculation, I now know, if I stopped here, how many moles of that salt are actually present in 100 milliliters if the concentration is 1.2 molar. So if I stopped everything, I would be able to tell you how many moles of the total solute. But that's not what they're asking, is it? They're asking you to determine the number of moles of the ferric ion, just the ferric ion. This is why we wanted to pay attention to the ionic formula, because I wanted to know what the mole ratio was. If I have 1 mole of the salt, so I'm going to put it down here so that I can cancel out moles of ferric sulfate. And put this down here. If I know I have 1 mole of this salt, by looking at that ionic formula, I see that I have 2 moles of the ferric ion. And they're asking me for how many moles of the ferric ion are actually present in that sample. So the moles of the salt are going to cancel, and I'm left with just moles of the ferric ion. And that's what they're asking for. So if it helps you to circle the last unit standing and then look back at the question and say, did I answer what they asked? Then feel free to do that. Cross everybody else out, right? And then what are we going to do? Well, I'm going to take 100 milliliters and I'm going to multiply it by the 1.2, and then I'm going to multiply it by the 2. I'm going to divide this whole thing by 1,000. So I got, with, let's see, how many sig figs? 2. I'm limited by the concentration. So there's 2 sig figs in that concentration, that 1.2 molar. So I got 0.24, and that'll be moles of just the ferric ion. And you know, they could have said, how many moles of sulfate are actually in there? And then you could have done the exact same calculation, but instead of saying I've got 2 moles of the ferric ion in 1 mole of the salt, you would say I have 3 moles of sulfate in 1 mole of the salt. So in a 100 milliliter sample of a 1.2 molar ferric sulfate solution, I have 0.24 moles of the ferric ion, and I have a totally different number of moles of the sulfate anion, right? Because it's not 1-to-1. There's 3 moles of sulfate for every 1 mole of the salt and 2 moles of the ferric ion for every 1 mole of the salt. So just keep that in mind, right? When that particular salt dissociates, floating around in solution, then you've got a different number of moles of each ion. All right, so let's just take a little bit of time to talk about the difference between dilution and concentration. So it's not going to be too tough to imagine. That dilution is equivalent to the addition of solvent to a solution. But what's actually happening is you're decreasing the ratio of solute to solvent, but you are not eliminating moles of the solute, right? So for example, I could take, say, 10 drops of like lavender oil or something, and I can bring it up to 200 milliliters. So are you one of those people that has one of those roller things and you want to make like a roller perfume with some sort of essential oil? You're probably not going to take the essential oil and just like dump it on your skin, right? You're probably going to dilute it with some carrier oil. Like you could take 10 drops of lavender oil and bring it up to 200 milliliters with enough water for, say, a diffuser, or enough avocado oil or whatever you're going to use for your little roll-on thing, right? But you're not using 200 milliliters of water for the diffuser. You're using enough water. So it's going to look a lot like it's 200 mils, right? If you're only using 10 drops of this essential oil. But that 10 drops actually takes up a certain amount of the volume. So if you're going to take those 10 drops and they are concentrated and you're bringing them up to 200 mils of total solution, you're adding some sort of solvent, right? So you're diluting your essential oil. If we're going to concentrate something, you're actually removing solvent from the solution, but you're not getting rid of any of the solute. So for example, if I wanted to heat up, say, some sort of like raspberry sauce to pour over a key lime pie, which you should totally do sometime, by the way, it's awesome. You're going to heat up this raspberry sauce, and sometimes people say, let's reduce it. That's actually not entirely chemically correct, but they'll use the terminology, let's reduce it, or they'll say, let's cook it down. What happens? Well, you're going to be cooking off some of the water, probably, in the sauce, right? And you're going to end up reducing the volume. But do you see raspberries floating away? Nobody sees that. So we have all of the components, all the solute to the sauce stays in the pot. But the water is being cooked off. It's evaporating, right? And you're making it thicker. So you're removing the water, but you're keeping the rest of the sauce parts. So you're keeping the moles of the solute constant, but you're shifting the amount of solvent. So if you're going to concentrate something, what you're going to do is you're going to remove some of the solvent such that the volume of the whole solution decreases, but the moles of the solute stay the same. So the molarity will increase. If you're going to dilute something, you're not messing around with the number of moles of solute. You're adding more solvent. So you're increasing the volume of the total solution, but you haven't changed the moles of solute, right? So you are decreasing the molarity or the concentration. But the one thing that stays the same, and it's going to be a big deal for us to pay attention to this, is that the moles don't change. The number of moles do not change if you're diluting something. The number of moles of the solute do not change if you're concentrating something. So since we can go ahead and say, well, if the moles are going to stay the same, the moles of the solute, and the molarity is defined to be the moles of the solute, right? Moles of the solute divided by the liters of the solution. Then if I were to take the concentration and say multiply that by the volume of the solution, I could figure out how many moles of solute I had. And if I know that no matter what I'm doing, if I dilute it or if I concentrate it, I'm keeping the moles of the solute constant, I'm just varying the volume, then I can say, if I take a look before and after, and I know that I kept the moles constant, and the moles are going to be equal to the concentration times the volume, then the concentration times the volume in the before snapshot are going to equal the moles of the solute in the before snapshot, and the concentration times the volume in the after snapshot are going to equal the moles of the solute in the after snapshot. And if we're telling you that the moles are not changing, then that means that the concentration times the volume in the before snapshot must also be equal to the concentration times the volume in the after snapshot. Two things that are equal to the same thing are equal to each other, right? So if, for example, I'm saying that the initial concentration times the initial volume are going to be equal to the initial moles and the final concentration times the final volume are also going to be equal to the initial moles, then those two things have to be equal to each other. This is going to be really handy for us. So let's try a little calculation. What volume of a 6 molar aqueous sodium hydroxide solution should a student use to prepare 200.0 milliliters of aqueous sodium hydroxide solution? And that final sodium hydroxide solution is going to have a concentration of 0.100 molar. for their titration experiment. This is a really common thing to ask a student to do because we will go ahead and prepare a concentrated stock solution. So this right here is your stock solution. So this right here is your initial concentration. They want to know what volume of that needs to be used to prepare 200 milliliters of an aqueous solution that has a smaller concentration. So essentially, they're asking you to calculate how much of this stock solution you have to use to make 200 milliliters of a final solution with a concentration of 0.100 molar. So this is going to be your final concentration. So if you want to go through the problem and read the words and figure out what's what, probably not a bad idea when you're first starting out these calculations. Another way that I like to do these calculations is I say, okay, I am diluting something for sure. I'm going to write down the dilution equation so that I know what I need. My initial concentration times my initial volume is going to be equal to my final concentration. Sometimes we call it M1 and M2, or MI and then, MF, whatever you want to call it, as long as you know what it is. And then I say to myself, well, they are actually asking me to calculate what? The initial volume. So what if instead of just saying, I don't know what they're looking for, you say, I'm going to take that equation and I'm going to make a little list over here. I list every little thing that's in that equation on the side. And then I look back through the problem and I see what I know. They told me that the stock solution had a concentration of 6 molar. They asked me how much of that I was going to use. So right away I see a big question mark because I don't know how much. That's what they're asking me to calculate. The next thing I see is that my final volume is going to be 200 milliliters. So 200 milliliters. And I also see that the final concentration they want me to make is 0.100 molar. Now, you might be sitting there going, all right, I notice you have mixed units. Big M, so molarity, is moles per liter, and you have milliliters. This might be one of the only times where it's probably not going to be a big deal if you don't convert the milliliters to liters. I'm going to show you why. But first, let me rearrange this equation so I can isolate the thing that I'm looking for. If I look at my list, it's like a little recipe over there. Those are my ingredients, right? And the only thing I'm missing is that initial volume. So algebraically, I'm just going to rearrange this equation to isolate V1. So if I divide both sides by M1 to get it off the left over there, I've got M2 V2 divided by M1. Right? I'm going to divide both sides by M1. So my initial volume's hanging out all by himself over there. And then what I'm going to do is I'm going to fill in my data. I see that my final molarity, or M2, is 0.100 molar. My final volume, V2, is 200.0 milliliters. And then I need to divide this whole thing by M1. They give that to me as 6 molar. Do you notice that these big M's are going to cancel out? And it does not then matter, unless they ask you to solve for the volume in liters, it is really not a big deal that you just leave it in milliliters. Sometimes it's actually a little bit more convenient, right? Because we might get a pretty small number. So in this case, I've got 0.1 times 200, and I'm going to divide it by 6. Yeah, that's going to be a small number, right? So if I had it in liters, it might be just a little impractical if you're the person standing in, the lab doing this work. So 0.1 times 200 divided by 6 is 3. in 1 sig fig, right? Because I'm limited by the 6 molar, and it'll be milliliters. But 3 milliliters of what, right? It's 3 milliliters of that concentrated sample. It's like I have a bottle of sodium hydroxide, an aqueous sodium hydroxide solution, and the label on the front says that the concentration of that stuff is 6 molar. I'm going to stick a syringe in there, and I'm going to suck up 3 mils of that 6 molar stuff. I'm going to quantitatively transfer it to a volumetric flask, and I'm going to add enough water such that I have a total final volume of 200.0 milliliters of my new sodium hydroxide solution. If I do that, I should have a final concentration of 0.100 molar. Does that make sense? So that's really what that 3 milliliters is telling you. It's how much of that stock solution you're going to add to enough water, or in other words, add enough water to that stock solution to come up with that final volume that has a final concentration of 0.100 molar. So there's a bunch of different ways you can word it. What you are not doing is you are not taking 3 mils of a 6 molar aqueous sodium hydroxide solution and then adding 200 mils of water to it. That's what you're not doing, right? Okay. So you will not have a concentration of 0.100 molar if you do that. Okay, let's try another one. So we've got a 4.25 milliliter sample of concentrated hydrochloric acid. And so I've given you the molarity or the concentration of concentrated hydrochloric acid. Because hydrogen chloride, by the way, is just HCl. And it's a gas, you guys, at room temperature. Hydrochloric acid, on the other hand, is an aqueous solution of hydrogen chloride dissolved in water. And so that's where you have to have this concentration, right? It is 11.8 molar. We're going to take 4.25 milliliters of it, and we're going to dilute it to 250 mils for use in isolating casein from milk. Casein is the protein in milk. Anyways, so what we're going to do here is we're going to calculate the final concentration of the acid solution. So first I want to identify what I know. I know that I'm going to do a dilution. And so I'm going to write down my dilution equation. M1 V1 is equal to M2 V2. What does that mean? It means that the initial concentration times the initial volume is going to be equal to the final concentration times the final volume, because the number of moles initially is going to equal the number of moles at the final step, right? And so those are both equal to each other. So the concentration times the volume initially has to be equal to the final concentration times its final volume. Then I'm going to make my little list so I know what I'm talking about. M1, V1, M2, V2. And I'm going to go back to the problem. I'm going to find all of this information. They are telling me they're going to take 4.25 milliliters of a concentrated hydrochloric acid solution. So my initial volume is 4.25 milliliters. My initial concentration is 11.8 molar. Then they say, what is the final concentration? So I don't know what M2 is, but I do know that I'm going to make 250 milliliters of total solution. So that's how I went through the problem, and I just sort of assigned all of those data to these little variables that I've just made up, M1, V1, M2, V2. Okay, the next thing I want to do is I want to make sure that I'm solving for the right thing. I want to know what the final concentration is going to be. So I'm solving for M2. So what I'll do then is I'm going to divide both sides by V2 so I can isolate M2. So M1, V1 divided by V2 is going to be equal to M2, right? We divide both sides by the final volume. It's going to be going away on the right, and we'll have M1 V1 divided by V2 on the left. And then I have my final concentration all by itself. Okay, so what I'm going to do, plug in my numbers here. I've got M1 is 11.8 molar. And my original volume, and I know they're mixed units, but again, it's not going to matter when the volume units cancel out or divide to 1. So 4.25 mils. Then I'm going to divide this whole thing by the final volume, 250 milliliters. So the milliliters are going to cancel out or divide to 1, right? And so, by the way, you guys, we're limited to 2 sig figs here because 250 with no decimal point after it only has 2 sig figs. So this is going to be my final concentration, and this works out to 0.20 molar. And that is going to be my final concentration. So 0.20 molar has 2 sig figs. That 0 to the right of the 2 is significant. In the number 250, there are only 2 sig figs because there's no decimal point, and that trailing 0 is not significant. Only the non-zero digits, right? Just a little reminder of our sig figs. All right, so we're going to move on from molarity and just briefly talk about different ways that we can actually express solution concentration. So molarity is just one way. There are a bunch of other ways. You guys will probably deal more with these in detail in Chem 32, but I do want to introduce them to you in Chem 31. So we're going to cap this video off right here, and then I am going to introduce you to some other expressions of solution concentration.